I'm truly delighted to introduce our keynote speaker. He's DHUG 2016 about an ontology he wanted to create, and now 5 years later, he's back and will update us on the changes and the current status of the need for such an ontology, and I hope on his progress. So Moriba Jah is an associate professor of aerospace engineering and engineering mechanics at the University of Texas at Austin, where he is the holder of the Mrs. Pearlie Dashiell Henderson Centennial Fellowship in Engineering. And I think, Frank, you might need to bring Moriba up to the stage for me. He's the director for Computational Astronautical Sciences and Technologies, a group within the Odin Institute for Computational Engineering and Sciences, as well for Space Security and Safety Program at the Robert Strauss Center for International Security and Law. Keep reading. He's got his bio fills a whole page. Moriba came to UT Austin by the way of the Air Force Research Laboratory and NASA's Jet Propulsion Laboratory prior to that, where he was a spacecraft navigator on a handful of Mars missions. Moriba is a fellow of multiple organizations, including TED, American Institute of Aeronautics and Astronautics, the American Astronautical Society, the International Association for the Advancement of Space Safety, the Royal Astronomical Society, and the Air Force Research Laboratory. He has served on the U.S. delegation to the United Nations Committee on Peaceful Uses of Outer Space and is an elected academician of the International Academy of Astronautics and has testified to Congress on his work as related to space situational awareness and space traffic management. All right, give me a second. I'm going to try to. Frank, can you see what's going on? Okay, Moriba, you may need to turn your microphone and camera on again. You're in the speaker tab, so you should be good to go. Moriba is also an associate editor of the Elsevier Advances in Space Research Journal and serves on multiple committees, including the IAA Space Debris, AIAA Astrodynamics, IAF Astrodynamics, and the IAF Space Security.
Booyah.
All right, booyah, we got it going on. Okay, there we go. All right, Moriba, please feel free to share your screen and start anytime.
Good day to everybody. No matter where you're at, hopefully everyone is safe and healthy. So I want to talk to you kind of about where Astriagraph is today. I got invited to give a talk about digital twins and that sort of stuff, which I think is germane to this, to show you Astriagraph as it is today since the last time that I was so honored to be able to speak to you about it. So we've come a long way since then. All right. So we have this thing called the space domain. What is this stuff? It's a combination of things. It's a space environment with charged particles and other particulates, and the sun's doing stuff. There's this thing that we call a gravity field, very dynamic, okay? And in this environment, we also have objects. Some are natural, some are human-made, anthropogenic. We have sensors, information sources. We have people, not just astronauts like, physically in space, but people that direct satellites and all these things. We have laws, rules, regulations. We have culture, ethics. So all of these things form the space domain. It's not just what's physically in outer space. It's all of these things that contribute to it in some way, that touch it somehow. It's the textbook definition of a complex system in that, even though there is chaos, driven by randomness, there is some structure, which has complexity to it. There are a growing number of participants in this domain. They behave independently from each other, by and large. And so that's an issue. There are causal relationships that are very nonlinear. If you've heard of the butterfly effect, basically small causes can have huge consequences. And the emergent behavior in the domain is not explained just by adding behaviors of individuals. So that emergent behavior also, because it's not explicable as just through superposition, it also lends itself into this definition of a complex system. And oh, by the way, even common treaties and laws can be implemented quite differently from each other. And so that also basically contributes to complexity. So kind of the raison d'être, or reason of being for space domain awareness, is we want to be able to make decisions about stuff in space. And we want to maximize decisions that lead to desired outcomes. We want to try to prevent anything, quote unquote, bad from happening to satellites, services, capabilities, and these sorts of things. Interestingly enough, within the United States, and certainly within the Department of Defense, is this model called the OODA loop. And OODA, this person, John Boyd, I think in the 80s, kind of came up with this. I mean, this model has existed for a very long time, but he coined the phrase OODA. And so it's observe, orient, decide, and act. And I will say, from my perspective, a lot of people, when it comes to space, have OODA loops, not OODA loops. They have observe, decide, and act. The orient part is key. And I think this is exactly where I want to focus it, for this, for all you folks that are into, data modeling, engineering, curation. Is the orient part is probably the most critical part of all this stuff. Just having a bucket of observations and sources of information by itself is not useful. These things need to be mapped into a way that can be easily accessible, that are in relevant, common lingua franca, timescales, reference frames, these sorts of things. So one of the mantras that I tell my students is, if you want to know something, you have to measure it. And if you want to understand it, you have to predict it. And I want you to keep that in mind. So decision intelligence in a complex system. We have, data exists everywhere. Information, content exists when we ask very specific questions of the data. There could be zero information content with respect to something that we want to know, but the query is the key. There's zero information until we ask a question. I want you to please keep that in mind. Data exists everywhere. Information is only quantified once we pose a question to the data. And said data may or may not have information related to the stuff we want to know, but it's all driven by what we want to know, the queries. We're interested in the entire population of stuff comprising the space domain. But as a whole set, that's not measurable. So back to if you want to know it, you have to measure it. That means that we can't know the space domain. So we have to rely on this thing called inferential statistics. And we can only know samples of that whole. And we have to make decisions under uncertainty. So that's a key thing, okay? We'd love to be able to predict everything that's going to happen in the domain. That's what we're kind of driving towards, because, again, if we can predict stuff really well, that kind of shows that we understand what's going on. We have categories of information. You've heard this in the news, probably related to geopolitics, that sort of stuff. But for stuff in space, we also have to consider these categories, whether the information is true or false, if there's intent to harm, an intent to hide, and the decisions that we make with the information at hand can be greatly driven by the category of information. So the question is, how does this, if you want to know any of these things, you have to measure it somehow. Back to if you want to know it, you have to measure it. So when we don't share information, when we don't have information that is widely and easily accessible, partial knowledge can lead to wrong decisions. And I've seen it time and time again, folks arguing tooth and nail about some common thing, but they each have their own perspectives. And maybe the information that they have is orthogonal to each other, but, you know, complementary. So we should be in the business of trying to assemble, aggregate as much information as possible so that we can have the most complete picture, you know, in front of us of the things that we want to know. Outer space may be infinite, but near Earth space is actually a finite resource. We have specific orbital highways that we put stuff in, and I'll show these things to you. You know, visualize, you know, Astriagraph visualized. Interestingly enough, you know, the knowledge about stuff in space, because a lot of that is scientific, we can say it's more common. But the implementation of that knowledge, the practice, is very individualized. So the knowledge base is more common across humanity. The practice is very individualized, and therein lies part of the problem. What we'd like to be able to do is assemble some norms of behavior, you know, that have maybe some ethical implications and that sort of stuff, so that we can try to make the practice of space operations also more common. Can we extend common knowledge to common practice? And that only happens at this intersection of, you know, these norms of behavior. So 3 things that this space domain awareness needs to provide to make decisions that lead to desired outcomes is, whatever it is that we do, it needs to be able to make space more transparent. What is it? Who does it belong to? What could it do? It needs to be able to make the domain more predictable. What's going to happen tomorrow, 3 days from now, a week, a month, years? Given a common situation, how will any given 2 entities react or behave as a consequence of that common situation? How are people interpreting laws and treaties, that sort of stuff? And accountability. Can we develop a body of evidence that can be used to hold people accountable for their behaviors in the domain? So those are the measuring sticks. Can't manage what you don't know what you don't measure. People keep on wanting to know what's normal behavior in space. Well, it depends on who you ask. It depends on who the actors are. Unfortunately, anomalies are difficult, if not impossible, to attribute cause to, because we don't have ubiquitous sensing. We don't have persistent monitoring of the domain. That, you know, inserts ambiguity, uncertainty. There's a lack of transparency in space operations. Not everybody wants to communicate openly what they're trying to do in space. And then there's the question, debris or not debris. That is the question. One of the ways that I like to think about this stuff is to kind of couch this in a kind of a Johari window, SDA, space domain awareness. And so, you know, this is going to be a you know, Donald Rumsfeld moment with the known knowns, known unknowns, that sort of thing. But aside from being a bit kind of comical, just, you know, using these terms, there's some reason to it. And ideal decision making comes when everything is a known known. Okay. And so I think a good way to look at this is, you know, there's stuff that you measure and there's stuff that you're aware of. Okay. So the first term is your awareness, and the second term is what has been measured. Okay. Think of it that way. When it comes to known knowns, that means that you're aware of the stuff that you've measured. It's real knowledge. Okay. But there are things in the domain that we know that we do not know. Okay. So we are aware that we have not measured certain things. It might be solar flux. It might be compliance of space actors with specific laws, that sort of stuff. And so we can ascribe uncertainty to the fact that we are aware that there's stuff that we have not measured. And at least that allows us to kind of quantify probable risks and impacts of that. The 2 bottom ones are key. and this is where big data science, analytics, and that sort of stuff has a role to play, because when we try to aggregate disparate sources of information and link these, what we're really trying to do is we're trying to maximize our knowledge. And again, if you don't measure something, you can't know it. So the unknown unknowns, right? Those are the enigmas. It's stuff that we're unaware of and have not measured. By aggregating large quantities of disparate sources of information, we're trying to convert those unknown unknowns into unknown knowns. Basically, we're trying to say, in this aggregated data set, did we unknowingly measure something? And the only way to know that is through queries, by posing questions. So by asking aggregated, curated data, specific questions, we get to discover things that we had no idea that we knew. Back to the first term is awareness. The second term is what you've measured. So the unknown unknowns are things that we're unaware of having measured. This data mining, this discovery process is what then allows the unknown knowns to get mapped into this ideal decision-making process. So our entire OODA loop, if you will, is really trying to structure Astriagraph to not only be relevant to the things that you're aware that you've measured, but being able to quantify the things that you are aware that you have not measured, and through big data, science, and analytics, convert the unknown unknowns to a discoverable set of unknown knowns and map those to known knowns for ideal decision making. So digital twins, new buzzword in various communities. And, one of the cool things that I took from interacting with you some years ago was this idea of kind of a digital library. And it was like, okay, it became very clear to me that I wanted to separate the knowledge base from the user base. Just like a library separates the knowledge from the user base, it's like, rich and poor people, young and old people, people of very disparate needs and curiosities can all go to a common logosphere, a common place to acquire knowledge, a library. So I wanted to replicate that. I wanted to say, I want to have a digital library for the space domain that assembles and maintains and curates all this knowledge and expose a common set of knowledge that is now consistent to a very wide variety of user needs. And so the other thing that this digital twin needs to have, not only does it need the library, but it needs the actual models of the space environment, the objects, the sensors, even decision-making criteria. So this is very different. When you try to create schema or ontologies for this stuff, having the actual scientific models embedded in this is fairly unique. We also want to be able to ascribe uncertainty to the entities, in the schema, in the knowledge graph, and understand that randomness and ignorance are not the same. They're not equivalent. They should not be used interchangeably. Whatever hypotheses that we come up with, they need to explain past observations. They need to be useful to predict the future. And it needs to incorporate the soft sciences. It needs to put things into context, geopolitically, culturally, legally. An example of things that are measurable, we want to be able to use. So here's like from physics sensors, we have a variety of things on the far left that we measure. So what combination of those things give us insight into the physical properties of stuff in space? What combination of those now give us insights into functional operational properties, and can we move further to the right with a taxonomy or a classification scheme for these anthropogenic space objects? To date, we have yet to actually develop a scientific taxonomy for human-made stuff in space. It does not exist. So many of you here are familiar with resource description framework, knowledge graphs, that sort of stuff. So this is just an example of different types of schema that we have been trying to implement in Astriagraph, again, to describe each one of these things: the sensors, the environment, the things on orbit, behaviors, and bring information that we can map into this to link it to, again, go from unknown unknowns to unknown knowns to the known knowns. Okay. In essence, what we have is we have a 3-layered system. We have the instance data, raw source of information on the bottom. The most difficult part, the long pole in the tent, is developing interpreters that can then look at the data and the metadata and map that into the schema that we have, and expose the mezzanine level to applications that can then run analytics and do clustering analysis and all that stuff. And so an example of that is, and we actually don't use RDF in Astriagraph, we just use schema, labeled schema. And so this is just an example, right? The entities are nodes, and the edges or lines are relationships between these. So let's see some examples of one source of information to serve many needs. So some people came up to us not too long ago, specifically people in the astronomy community, are like, hey, there are these things that Elon Musk is launching called Starlink satellites, and they're actually reflecting a lot more light from the sun than we expected. And we kind of don't like that because it's basically nuisance parameters. It's clutter in our astronomical images. It actually has detrimental consequences to astronomy, to ground-based astronomy. So basically what you're seeing here is you're saying, okay, here's the physics of incident light, photons from the sun interacting with a surface and then scattering diffusely or specularly at, mirror-like. This is kind of what the Starlink satellites kind of look like. And basically, again, the sun is reflecting light off of these objects in the direction of ground-based telescopes and basically interfering with the natural phenomena that they want to observe. So I'm going to show you, here's a movie that our group created for astronomers that actually pulls information from that we curated within Astriagraph to do this analysis. And what you're going to see is you're going to see predicted light pollution for basically, this is going to be for an astronomer in Chile. And this plot right here is if you were standing at the site and looked straight up, right above you, and then northwest, southeast. This is a sphere that surrounds the Earth. So we call that a celestial sphere. And you're going to see stuff in the general direction that the telescope is pointing. And then this bottom one is as if you were standing at the site. And the gray area are regions below the horizon that the telescope can't see. Okay. The color code is visual magnitude. The dimmest that you can see is probably around 6. Larger numbers are dimmer things, but telescopes are light buckets to dim things, right? And basically, the reason you see streaks is the cameras, these charge coupled devices, open up their eyes for some amount of time, maybe like a few seconds. And so you see an integrated signal. This is how much light they collected over that integration time that the shutter was open. Each one of these streaks is a human-made object in space reflecting sun towards the observer. So it's in the visible range. And this is what astronomers have to contend with every night. You're going to see a bunch of, we're going to start at dusk, you're going to see these things look like they disappear, but they're not really disappearing. So this is what ground-based astronomy has to deal with on a nightly basis currently, okay? As we go into the night, these objects begin to reflect less sunlight because they're going through Earth's shadow. They're being eclipsed by the Earth. You only see things at high altitudes reflecting sunlight. And then as we progress through the night, so this is like around midnight, now we're going to start going towards dawn, and you're going to see the swarm of stuff reflecting sunlight again. Again, the satellites aren't disappearing. They're just going through Earth's shadow. They're being eclipsed. So you definitely don't want to schedule stuff apparently at dawn and dusk, right? Those are the worst times. But sometimes astronomers need that. So that's a current reality of ground-based astronomy, and it's not going to get better because we keep on launching stuff into space. A separate user said, okay, look, we want to flatten the curve on the growth of orbital debris, orbital pollution, and the main contributor to the pollution in space is, as with COVID, people just aren't complying with what scientists say that they need to do, like social distancing and masking. People aren't complying with guidelines that science has said, do these things to mitigate the growth of debris. So part of, again, you can't manage what you don't know, and you don't know what you don't measure. So can we measure compliance of space actors with some of these guidelines? So we took that upon ourselves. We developed some schema relevant to that query, and those are the websites that you can go and kind of check that out. Interesting stuff, and maybe I might show that to you here in a little bit. But yeah, it turns out that there's a high degree of non-compliance, and we can now have a public-facing website that shows that. Another user that's different says, hey, I want to be able to assign a first and last name to stuff in space. How do I do that? Well, if most of the objects up there are dead, so they're not transmitting their identity. So basically you have observations at different times collected by different people that, you have no idea what the identity of the objects are. So there's an identity crisis in space. How do we solve that? So we've been looking at getting inspired through biometric recognition techniques. Can we develop a system that collects information remotely on objects in space and puts them through an equivalent enrollment verification and identification process? We're going to exploit the fact that we know that photons are interacting with surfaces of objects and getting reflected towards observers. We call these things light curves. Here's an example. This satellite Topex is in low Earth orbit. It's dead, it's tumbling. So we collected 11 minutes of data. Brightness is coming out of the page, intensity of photons being reflected. And this is, assuming the body frame is fixed, just rotating around the body frame. This is what this axis is. So this is going around the body. So you can see diffuse reflections, and these are more mirror-like or specular, okay? So this is from Topex. This is real data. And we're exploiting, again, diffuse and specular reflections from Topex. So what we do is we say, okay, now we have this light curve. Imagine that we have a unit sphere around the object. Let's develop a heat map of where photons were reflected in the body frame onto the sphere. And then let's project that in a Mulvide projection, which is a 3D representation of that sphere, and see if we could use that as a fingerprint. And here you go. Here's a partial fingerprint of Topex collected on this evening. The parts that you don't see data are the parts of the satellite that we did not see, but you can see some interesting things here. This is a diffuse. Here you have more mirror-like things that you can see here. And the question is, are these persistent features? And here it is. You have 2 different nights of data, independent data collected, and these things don't look identical, but they look similar. And so we are in the process of also using Astriagraph to curate and model fingerprint information about stuff in space. So I am going to end the show there, but what I want to do is bring this up. Let's see. Because you might say, okay, you talked about anthropogenic space objects and pollution, blah, blah, blah. These are just words. All right, so here we go. So hopefully here you can kind of see Astriagraph visualize. Every single dot is not to scale, it's just location of stuff. But here you can kind of see each one of these is a human-made, human-derived object currently being tracked in Earth orbit. Here we can see low Earth orbit. You can see this string of pearls here. I'm going to zoom in here. This is like this chain of satellites are all Starlink satellites from SpaceX. Let's see. Oh, sorry, flocks. So these are actually from Planet Labs. So Planet Lab has downward-looking stuff. You also have trains of these kind of satellites. Like, let's see. Here's one train of satellites. You can kind of see these. They're currently, these were probably the latest launch from the Starlinks, and see, yep, there you go. And so these things will separate over time, and it's for our own good, right? It's for global internet. So let's embrace the space traffic that goes along with having global internet provided by space-based capabilities. So that gives you an idea of some of the traffic and stuff. But if that weren't good enough for you, then we also have this right here, which is a 20-minute prediction of things that are going to crisscross each other, within 6 miles. So over the next 20 minutes, these are the predicted conjunctions or near misses for objects, any pair of objects from like 20,000 objects that you see here, 19,825. So over the next 20 minutes, which pair of these are predicted to come within 6 miles of each other? And whatever those are, show me. So green dots are things that both objects are working. Red dots are things where both are dead. Yellow dots, one thing's working, one thing's dead. Histogram altitude, about 800 to 900 kilometers, kind of the altitude where China blew up one of their satellites in 2007, creating a lot of junk for a very long time, unfortunately. And then relative speeds, the relative speeds of these crisscrosses are 15 kilometers per second. That's 15 times the speed of a bullet. Let me tell you something. Even when small things like a bullet hit satellites at 15 times the speed of a bullet, bad things happen. And so the services and capabilities that we depend on are not protected from harm, loss, disruption, or degradation. So that's a thing. And one of the last things that I want to show you before I kind of open it up here is we also, again, have Astriagraph be able to not only provide this orbital information and that sort of thing and help with collision prediction stuff, but also these queries on compliance, non-compliance. So if you went to this website, you might say, okay, show me some records of non-compliant things. Let's say 2019, let me just click that and see what happens. That should be going to the Knowledge Graph database at the Texas Advanced Computing Center, and then say, okay, here are the objects that are non-compliant, that we measured as non-compliant in 2019. I can go to tabular results here, and we also have information provenance schema. And so, yeah, so this, now you can query this and it'll tell you what orbit, catalog ID, how's it, country, this is Thailand. If it has a known area to mass, it'll put that sort of thing there. So that's non-compliant. Here's India, non-compliant. Here's People Republic of China, non-compliant. The United States, non-compliant. Russia, non-compliant, so on and so forth. So that's public-facing website. And then we can also say, hey, there's also a treaty on registering objects with the United Nations. How compliant are people with that? When you look at the UN registration treaty, it says register your objects. If you're a launch state, please register your object as soon as is practicable, okay? As soon as is practicable. Those are the words used. All right. So this is looking at people that registered in 2019. So that's the locations. You can click on an object, kind of see the orbit, all that stuff. Let's go to these tabular results. Again, this is a public-facing website now. Interestingly enough, when you see this stuff, as soon as it's practicable is actually widely interpreted, it turns out. You would think that, you know, from the moment, so one of the things that we did, because we ingested all of the information from the United Nations website on Space Object Registry, we have that as instance data. We mapped it into our schema, into our ontology to be able to do these queries. And we basically ran an analysis that said, let's define the lag time as the time between launch, you know, the birth date of the object, and when it was actually submitted to the UN registry. Here's France, for instance, right? Not to pick on France, just the first object that came up. 1,916 days. Just to refresh our memory, you know, 365 days is a year. It's taken people years to just submit something to the UN after the thing's on orbit. Sometimes even after the thing is already dead and is not working anymore. This is how countries are interpreting registration. One thing that we decided to do is create a rating system, because I love that. So I said, okay, I'm into the 5-star rating system for restaurants and hotels. Let's come up with a rating system and say, you get 5 stars if you register within the first, say, 3 to 6 months. You get 4 stars if it takes you a year, or, you know, within 1 year. Within 2 years, you know, 3 stars, 3 years, 4 stars, above that, 5, okay? So this shows you by country how many objects each country registered and kind of what that rating is. And it favors people that have more objects. So if you registered your satellite and you only have 1 satellite, you did it within the first like 90 days, your rating isn't as good as maybe somebody that has hundreds that has done, you know, that sort of thing. So we have a weighting matrix that we can also publish, like, you know, what the algorithm is in the weighting. But nobody's done this sort of thing before and seen it in this way. And you can see by country how they've done in terms of how they're interpreting this common law, something that 100 plus countries ratified, and you can see that the interpretation is not common. So with that, let's see, what do I want to do here? With that, I want to stop doing that so that I can open it up. Hopefully that's been interesting.
I think it's very interesting for my part. And we do have a few questions. Thank you, Moriba, for sharing that. Jeffrey Gordon is pulling out his mathematics, and he says, I imagine, this came in really early in your presentation. I imagine since the behavior is nonlinear, it can tend towards chaos. Is the entire system chaotic, or are there local regions of stable orbits? Are Lyapunov exponents used to determine that?
Yeah, so the answer is yes. The answer is there are stable orbits. And I would say that, you know, in my opinion, the appearance of chaos is basically our ignorance. So I think that things are a lot more deterministic and less random, and we ascribe you know, randomness to cover our ignorance. So
also on regulated use, do you fear that we are getting dangerously close to realizing Kessler syndrome?
yeah, so you know, I'm actually not a fan of Kessler syndrome. Just for the people that aren't aware of that, it's kind of like this notion that, you know, there's some tipping point beyond which, even if you don't launch any more objects, there's going to be this kind of infinite cascading things are going to bump into each other. When two things collide, they become smaller objects, and that process will just kind of be this runaway train. My opinion is that Mother Nature, when left to her own devices, seeks equilibrium. And so I don't believe in the infinitely running, cascading collision kind of stuff. At some point, things become very small, relative speeds become small. You don't have that sort of thing. What I do believe in is that any given orbital highway has a finite capacity to carry traffic, so a carrying capacity. And I think that carrying capacity can be, or for some orbits has already been exceeded. And I think pragmatically what that means is that when the carrying capacity of an orbit has been saturated, it means that our decisions and actions are unable to prevent the loss or disruption of a service above, say, some threshold per month or per year.
Okay. How do you feel Starlink by Elon Musk is going to impact the usability of our local neighborhood of space?
I believe that SpaceX is doing what's legal, and they have worked with the astronomy community to try to minimize the negative impacts to ground-based astronomy. I think that the big issue is because we don't have sustainability metrics in place. So that means A, saying that near Earth space is a finite resource, and then B, coming up with these definitions that humanity can embrace in terms of orbital carrying capacity and something like a carbon footprint analog that I'll call a space traffic footprint, loosely understood as the burden that any given object poses on the safety and sustainability of other stuff. Until we have those metrics, I think we're in danger of a tragedy of the commons. And so, if we could have those metrics in place where we can start quantify the environmental impact of the existence of these objects on orbit, then I think it becomes much clearer to say, okay, maybe we shouldn't give 10,000 licenses for this thing. We should spread them. Then we have, a regulatory framework that we can bring to bear to even things out and make things more equitable and all these things.
A great deal of the OODA loop and space domain is temporally based. Traditionally, taxonomists and ontologists have not modeled time. What pitfalls do you see or concerns do you have with time?
Thank you. So I think that's a pretty cool thing that we've done with Astriagraph, is that just like entropy in the universe always increases, Astriagraph is always growing because we do keep timestamps on information, and we keep those historically. So whenever you want to figure out something about something in space, there is that it is not only, like you said, not just spatial, but it's spatial temporal, and we do keep tabs of that. So.
And expanding on that question, it seems that GIS would also be a challenge here since we can't track everything at once in orbit. Do you feel a classification system could help by constraining behavior?
Absolutely. And so I think that part of I think you hit it on the head. I think that different species of objects in space behave differently depending on their habitat, their orbital zip code or region. And I think if we could come up with a trait-based classification scheme for anthropogenic space objects and understand these in terms of these classes and species, given the habitat, I think that we would start, in a clustering sense, we would start seeing similarities amongst these, right? And then I think based on that, because we'd have similar behaviors with common species and common habitats, that would allow us to collect data more meaningfully, streamline things, even help with the regulatory process. Like all these things would be benefactors of having a trait-based classification scheme.
Okay, that's all the questions we've gotten so far. So I'm going to wait for just another minute or so to see if anybody else has questions. We have just 14 minutes left in this session before, as those of us who were here yesterday know the system shuts down and rudely boots everyone out. But if you could stick around for just a few more minutes and maybe people will come to the table and ask you their questions. Questions there.
Absolutely.
Okay. Oh, what is the biggest challenge in trying to communicate this to regulators?
I think that people still believe space is big. People still can't connect to space being a finite resource. Coining the phrase space environmentalist, one of the things that I'm trying to do is use terminology of environmental protection of Earth, ocean, atmosphere, climate, and extending that to describing stuff in space, making analogies to pollution of like microplastics in the ocean with small debris in Earth orbit and these sorts of things. I'm using the term, highways, lanes, these sorts of things purposefully to try to create that awareness. And I'm trying to communicate with folks through, op-eds and podcasts and these sorts of things in areas outside of space, just like with yourselves today, because I think space is, I'm trying to get people to migrate away from ownership more towards what I consider the original role of humanity, which is custodianship and stewardship, and remind people of that role of stewardship and custodianship and show people, hey, this has actually been put in practice by specific indigenous people around the globe for tens of thousands of years. We should probably listen to those tenets of traditional ecological knowledge and apply that. And I think in the measure that I can connect that, and by the way, we have a project called Eyes on the Sky. So if you go to like eyesonthesky.org, you'll see it. We're trying to create a mixed reality experience as well as a docu-series to basically massively enroll humanity in this vision and say, hey, space is not something to be idolized. You don't have to be an Elon groupie or an astronaut groupie. It's just an extension of human activity. We don't worship people that, drive boats or pilots anymore. We shouldn't be idolizing people that go to space, and space should not just be a place of interaction for billionaires and astronauts. So I'm trying to actually normalize that.
Okay. Can the same models be applied to climate change questions? Are they?
So I'm actually reaching out to folks that do environmental protection and other domains like maritime and that sort of stuff to see what commonalities exist and how can we borrow some of those to apply it to the problems that we see in space.
How can the taxonomy community help you in your efforts?
I don't know, because every time I put it out there for people to help me, it's like it's mostly crickets. I think there are various ways to develop a taxonomy. I think I like the trait-based stuff the most because it's back to, if you want to know something, you have to measure it, sort of thing, and just going based on measurable things. But yeah, I'm just kind of trying to make it up as I go along because nobody's paying me to develop a taxonomy. I'm doing it because I feel it's the right thing to do. And I'm trying to leverage my own research in like, can I discover threats to stuff in space or whatever? It's like, well, the taxonomy would help me, but it's very much at a snail's pace, unfortunately.
Okay. That was our last question. We have just under 10 minutes. So again, thank you very much for being here, and we'll go back to the tables.